Yep.
And then the stop signs are rare and gas station.
Yeah.
Garbage.
Another big thing is your guys' roads are. Some of them are fantastic, like the new asphalt roads that they've laid down. When they redid the road right outside the high school,
Those are great.
turn left,
Yeah.
magical. I love the asphalt roads,
Everything
but
else?
they're few and far between. Everything else, trash.
Try
You
going
guys
out-
have terrible roads.
Try going out on 26. Highway 26, I think that goes through Fairmount, but that's 26.
Okay.
That road's garbage all the way through. There's
Yeah.
not a big part on that road.
You
38th Street sucks on the railroad track.
Yeah.
Across the railroad track is horrible. You think
They
that's bad?
destroy your
You think that-
suspension.
You think that's bad? Go a block over because they were doing some work there, which never fixed anything. So I don't know why they blocked that crossing for so long.
Yeah.
But a block over, I kid you not, it looks like it belongs from like a Jeep Wrangler commercial of them rock climbing.
Oh my
Because it's
god.
like
Yeah,
the pavement's
the
like
train.
waved over the tracks. I don't know how a train goes through there.
Yeah.
Well, if you
I
hit the
can't-
tracks, going about 37, you're fine.
Hey,
Nothing else. I do it every night. I'm fine.
Interesting.
My
But anyway, in
car
Iowa, we don't have that. In Iowa, our roads are very consistent. It's more or less your typical concrete. It's not. They don't do the asphalt black tar stuff typically. But so not as smooth, but they're consistent. We have a lot of our highways, like our 55-mile-an-hour roads. They're either rural highways that are small town, low traffic, so they're nice, or they're major highways that are really paved and well cared for. Otherwise, we have interstates all over, right? So we have like major interstates, like big thoroughfares that are really, really nice that cut through Iowa. So if you get somewhere,
roads suck.
yeah, you can do nice highways or the interstates, which are amazing. So it's kind of weird to be here and.
Well, then like all the roads in Marion I feel like suck, but then most of them looks like a salon.
Your guys is like even like potholes. Potholes are everywhere. Your guys is like drainage, right? The manhole covers.
Yeah.
They're not even with the road.
No.
They just like poured over them and then cut out that hole and left a huge dip. So you got to like every time you go over, it's like what?
Yeah, it doesn't make sense to do that.
Yeah. But anyway, enough about that. So today's pretty straightforward. I think we can finish the notes. The last thing that we're doing is conservation of momentum, right? We're going to really dive into how is momentum conserved in certain situations. Is it conserved in any situation? Is there collisions that, things might run into each other? Is there ever a situation momentum is not conserved? We're also going to bring in our systems, right? The open and closed system, what type of collision. We're also going to bring back our idea of energy because that has an impact on the momentum. So we're going to talk about collisions and conservation momentum. I have a couple really good conceptual challenging questions. It'll be short, but I want to try and trick you. I want to challenge you guys. We'll think about them. And then the rest of class, I want us to give work time. I have homework. I'm working on it. There's one part that's really tricky algebraically that I want to show you. I'm going to try and give it away because it's taken me a while to crunch the numbers, so to speak. The rest of it's straightforward, but it's a bunch of little questions to kind of give you this full picture of how do I look at a momentum problem and how do I go step by step, or how do I figure out what is going on behind the question. So I want to give you work time to start that in class. That way if you get stuck, I can help you get on the right track so that you can finish that and practice for next class. Next class, we're on the border between we could take an extra day to do more practice, more review. However, we might be able to push it up and have 2 free days before break. I don't know. I'll wait and see, but we're close to testing. It'll either be Monday of next week or Wednesday. So Wednesday at the latest, we're going to take Unit 5 tests.
Wait, so are you saying that this Thursday you're thinking about doing more review?
We will review, but it could be review the day before the test and test Monday.
Okay.
It could be review, work through some stuff. Monday, we do final review, work through some stuff, and then test Wednesday.
So it's coming down to whether we take the test Monday.
Monday or Wednesday.
Okay.
Wednesday would be still on track, so I'm fine with that. I want to see how we feel. Yeah, but anyway, I just want to always include you guys on kind of my timeline and what I'm thinking.
And
So,
then what will we do on Wednesday, Friday?
so Wednesday, as of now, we would test. If not,
Yeah,
Wednesday and Friday would be free days. We could do, say, like Wednesday, strategize, plan for the AP test, maybe do some practice problems, casual review, but make use of our time. And then Friday, we could have a free-for-all, watch The Office, how it's made, hang out, just kind of, mini party, kind of to celebrate going on break. So we're in a good position. The other thing, I posted to Classroom, our second review session I want to do Wednesday. I have meetings and stuff Thursdays and Friday after schools.
That's what I was going to ask. What the heck, guys? Where are we all at?
I know, we didn't have many.
So whopping 3 of us with 1 online.
Yeah.
That's concerning.
Yeah, but anyway, our review session tomorrow after school, right? Tomorrow, right? Because I got stuff Thursday, Friday, so those won't work for me right after school. So tomorrow we'll do that review session. Please come if you can. I keep them really short. I was a little bit late. It was like 35, maybe 40 minutes. I want to do like half hour so that you're not here a long time. You can get some extra practice. The FRQs is the main thing that we practice. Those are those big, long, open-ended questions that are going to show up on the AP test. Those are really good to start getting a feel for. That's the main thing that I want to do in that review session. We'll slowly get that exposure to those FRQs so that when we get to the AP test, you're like, okay, FRQ, I've done these before. I know what they're looking for, right? But please come tomorrow after school if you can. It's to your benefit. If you can't make it, that's okay. You can let me know. I can send you the questions that we did. But if you can make it, please come. I'm going to try and keep it short. Try to do half hour and then get you out of here, get you home. Because I also want to get out of here and go home. So that's tomorrow after school. Right after school, just pop in my room. We'll knock some stuff out and be out of our way. Okay, so today, we'll put this away. I honestly don't remember exactly where I left off. I think I was here. So, whatever notes you get those out, I don't want you to follow along. There. Conservation. This is a big idea. This final piece is conservation of momentum. We've talked about momentum. We've talked about a change in momentum. What causes a change in momentum? That is momentum. How do I change momentum? You can either give me the name of the thing that changes it or the equation. Impulse. Good. Impulse. What is impulse equal to?
F and T.
Yes. Force times, it's actually delta T, right? It's how long the force is applied. If you apply a force for a certain amount of time, that is an impulse. F, the force, times the time you applied it, that impulse is what creates a change in momentum. It could either add momentum to the system or take momentum out of the system. Right? That's if we're applying force on an object. Conservation of momentum, again, conservation means prevention from loss, right? You're conserving quantities, you're keeping them, you're protecting them, you're not letting them change. So what we're looking at is how do we make sure that momentum stays the same? Maybe after a collision happens, that's the biggest thing. I don't know why it's in here twice. So right here, that was a collision. In that collision, the momentum of that system was conserved, right? Momentum coming in, momentum going out. The conservation of momentum means that the momentum in total is the same. It's conserved. Total momentum before, right, when they're coming towards each other, whatever you add up those momentums, that value is exactly the same as after they hit and go the other way. So you first have to look at, okay, what happened before? Well, ball A had a certain mass and a certain velocity. That's momentum. I need to add the momentum of block B, or ball B, coming in. Momentum, or mass, times its velocity. Add those two things together. That is my total momentum before the collision happened. Momentum is conserved. You don't lose it. It doesn't disappear. They don't destroy each other. It stays the same. Right? They bounce off and then they go the opposite directions. Well, they still have momentum. Block A has a mass and a velocity, now the opposite direction. Ball B has the same mass and a velocity in the opposite direction as well. If I add those two together, that total is the same as the initial total. It's just like our energy equation. When we had the conservation of energy, the kinetic energy beforehand equaled the kinetic energy afterwards. You didn't lose it. It might have changed a little bit, right? Your total energies, it could change, but overall it stayed the same. So formally, mass A times velocity A plus mass B, velocity B. Those quantities added together equals sum total momentum. Do the exact same thing afterwards. They hit each other and you got mass times velocity, mass times velocity. Add the momentums up. It's actually the exact same thing. Does this make sense? Momentum before equals momentum after. What's momentum before? Well, you got to add up the two momentums that you have. What's the momentum after? Add up the two momentums you have. Okay? This is the general equation for conservation of momentum. Almost always we're going to look at just two objects. Yeah, this one. This is the, simplified one. This is the actual equation, right? This is the main variables that you would actually know and plug in. Do the math and boom. Big thing, that idea. Your momentum is conserved. You don't lose it, you don't gain it, it stays the same. It stays within my system. Nothing's coming into my system, nothing's going out of my system, so there's no reason that anything would change. So even after they come in and collide, the total momentum of those two objects, that whole system, is constant. It's conserved. Now, let's look at a situation you might be familiar with. Firing a gun. I'm going to basically explain what's recoil. Why does your shoulder hurt after you shoot trap for hours on end?
That's the manifestation of guilt.
Of what?
There's a spring. There's a spring like right on the butt of the stock.
You have a spring?
So there's it has a pad and there's like these three little springs.
Oh wow!
They go like around this would be above the stock. There's like these three little springs. There's a rubber pad.
Nice.
So when it shoots, it pushes back.
When I was a kid, mine just had a big rubber pad, so
yeah.
Probably wasn't near as nice as that. But same thing is true. My system is the bullet and the gun. That's my system. When I shoot the gun, everything's coming from inside the system. Nothing's coming in, nothing's going out. So the momentum before and after of my system, it stays the same. It's conserved. The momentum of the gun to start with, and the momentum of the bullet to start with, well, those are zero, right? Before I shoot, there's no velocity in either the bullet or the gun. So the total momentum is zero. Then how do you explain conservation of momentum? Well, when you fire, this bullet is ejected forward. You now have forward momentum. Did you see the gun? Did you see the gun kick backwards? What happens if I have positive momentum and negative momentum and I add them together? Positive and negative, they cancel out. So sure, you have momentum that's created, but your system, nothing's created. You're conserving everything. That's why you have recoil. No velocity, no velocity. This goes to 0, just like that. Your math is easy. Anything times 0, 0. Anything times 0, 0. On the right side, however, your gun is pushed backwards. Really slowly, but it's definitely backwards. So you have negative momentum. Your little tiny bullet is shot forward at a crazy high speed. So you have positive momentum. Well, what happens if you do the math? Do you see that? 0 plus 0 is 0. Negative 2 plus 2 is 0. This shows you that even if something happens, if you got a closed system, you got nothing coming in or out, you have no reason for your momentum to change. Everything comes from inside the system. Now you have an impulse on the bullet, right? An explosion happens and it pushes that bullet for a certain amount of time until it's out of the barrel. But that force comes in equal and opposite pairs, right? That explosion pushes the bullet forward, but it also pushes your gun backwards. So you do have an impulse, but it comes from in the system that does equal and opposite. That's why you have recoil. Somehow to get that bullet moving forward, you have to have the same amount of momentum moving backwards. That's why you have to have all these systems, right? Like a rubber pad on the butt of your gun or springs. You have compression and gas release systems in the gun. Because if you think about it.
If you shot it without the rope, it'd probably just like dislocate your shoulder.
Yeah. It would hit your arm with the same momentum as that bullet.
So your shoulder.
Pass.
Yes. So you have to have all these systems to kind of divert the momentum outwards so that it doesn't go into your body.
It wouldn't break your shoulder. It definitely wouldn't feel good, but it would not break.
Yeah, it's just not good. But the reason that all those things were engineered is because momentum is conserved. You got to get rid of it or divert it to protect your body. Okay? Now, collisions. This is funny, but also not.
Oh, do you need a space on that?
No, like full-on chest.
Oh, I think you just smacked his face.
I have a video on my phone.
Watch that.
Oh.
Can you imagine how that would feel?
Okay.
Nice.
Okay.
I assume so. I don't honestly know. It was an old clip.
Okay, we can laugh.
First of all, he has momentum, right?
Yeah.
He has a mass and he is running with a velocity. Did you notice? Basically, I think he missed the trampoline or didn't jump. And obviously, you can't stop yourself on a dime. So he kept going and collided with the end of pommel horse. I think that's what that is. Right? Did you notice? Did you watch the pommel horse?
Oh, he missed it.
Did you see it?
Yeah, he missed
Did
it.
you see that huge bar that he was going to jump onto? It lifted up. So his momentum impacted and collided with something else. Basically, they traded momentums. Right? He had a bunch of momentum going forward and he was stopped dead. Well, his momentum was transferred into that pommel horse, which is a lot heavier than him. So it was given a velocity, but eventually gravity stopped it and pulled it back down. In a collision, momentum's conserved, but it could be transferred. It's the same overall, right? Bunch of momentum, and the pommel horse had none. After the collision, he had no momentum. The pommel horse had all the momentum. What do you think is going to happen?
They're going to blow up.
This is a perfect cancellation. You guys see that? Mass and velocity, mass and negative velocity. They have the same mass, same velocity. Or actually, we don't actually know that. Just know that the total momentum is equal. When you have two equal quantities, equal and opposite, they cancel each other out. That's why you come to a dead stop. Total momentum before and after is 0. This is an explosion. Joey, McKay, are you with us? So this is an explosion. Something blew up or exploded. They were together and it blew up outward. So initially you had no momentum. There was no motion. So of course you don't have momentum. But if I have an explosion from within the system, my total momentum is still 0. Nothing was coming in, nothing was going out. It's all within this 2-cart system. And if you notice, after the explosion, negative momentum, positive momentum, those add up to 0. The before and after is exactly the same. What about this? What if I have 2 different carts? I got a really heavy cart and then a normal one. What's going to happen when I have an explosion from within the system? I know momentum is going to be conserved, but what's going to happen? Like, describe what will happen of each of those parts. Aiden, what do you think?
The cart without anything on it will go a lot further.
Okay. So you're saying the lighter or the less massive cart will go faster and further than the really heavy cart?
Because it has to be equal, right? So
Yeah.
It's not going to push that one as much, then it'll end up displaying both.
Yeah.
But
You
the
could
someone's lighter will go further.
You could think about it in 2 different ways. One way is I have one explosion pushing both cars. You bet it's going to be easier for me to push the light cart rather than the heavy cart. So this guy's going to go zinging off. This guy will move a little bit. You can think about the forces, maybe the impulse within the system. You could also think about, okay, big mass, little velocity gives me something. Well, to equal that same value, I have a little mass. I got to have a big velocity for them to be equal. So watch. You see that? Aiden was right. This one went further, but more importantly, it was propelled faster. Say this is a kilogram at 3 meters per second in the positive direction. This had 3 times the mass, so it had 3 times less velocity. So you could see the momentum is still conserved. Nothing came in or out of the system, so the momentum doesn't have any reason to change. Something happened, but still, the grand finale total is still going to be 0 because it started with 0. This is where we get into 2 different types of collisions. This is really important to know, particularly to pay attention to on a question. The type of collision drastically changes what happens in the collision. What do you guys think? Well, like I said, it says it. An inelastic collision is when they stick together. They collide and now they're conjoined. So they're going to move together. That's an inelastic collision. You still conserve momentum. You'll find any collision, momentum's conserved. I want you to pay attention. Do you notice what the final form of the momentum equation is after an inelastic collision? Right? Say you got 2 things coming in together, mass, velocity. When they come together and stick, they're stuck together. They move together. That means there's only a single velocity because they're united. They're one object. Well, now you have a new mass. The new mass is part A, part B added together. That now has a certain velocity. And if you do these calculations, the momentum before and after, it's the same. It's conserved. This is the special situation for an inelastic collision. It should make a ton of sense. They stick together, they become one object. Well, what's the mass of that one object? It's add the masses of all the individual parts. We know when parts are cart 1 and cart 2, whatever it is. They move together, so they only have one velocity. So if they keep going, that's a plus whatever velocity. Momentum 1 and momentum 2 get merged together into a single momentum, and those quantities before and after are the same. Doesn't matter what it is, but before and after is the same. That's them sticking together. So look at the numbers. This situation, boom. They get glued together the moment they stick. So you can say, hey, 1 kilogram and 1 meter per second, 1 kilogram with no velocity. So your total is 1 kilogram meter per second. Afterwards, the combined new mass is 2. What's the new velocity? It's just an algebra equation. You know that momentum's conserved, so you know they're equal to each other. Just solve for the unknown. It's half the velocity. Makes sense. If you keep the same momentum and you're now creating a double mass object, well, to keep it the same, if you double the mass, you got to half the velocity. Should make a lot of sense. Also, the math literally will tell you, right? If you do the conservation of momentum, the numbers give you the answer, right? That's an inelastic collision. What about this one? Now I don't have equal cars.
Too hard.
Huh?
Too hard.
No, it's easy, right? Momentum 1 is 1 mass and certain velocity. Momentum 2, well, 2 times the mass, but it stands still, so nothing. Your total is still 1. But after there, it's inelastic, which means they stick. You just have one object afterwards. They get combined. The total mass is 1 plus 2 gives you 3. And you need to find out what's the final velocity after collision. That's about as easy as it gets for algebra, don't you think?
So a third.
Yeah, so your final velocity after they stick is going to be a third of the velocity from the original part. Bam. That one, it's really hard to, the animations aren't as good, but once they hit, they go really slow. Because now, they're combined, they have to share a certain amount of momentum, but they have to share it for an object that's now 3 times as massive. So your final velocity is 1/3. What happens if I have a really heavy car with twice the mass, right? And it's got momentum, and it's colliding with a light car going the other way? What do you think is going to happen? Are they going to collide and get pushed this way? Or are they going to collide and get pushed this way? Notice, they have equal velocities. So the velocity, there's no difference. They're on equal level or playing fields, right? Who has more mass? This car. So who's going to win? This guy. This guy is going to overcome and push it all to the left or to the right. Boom. He won because he had more momentum. However, the whole system, it didn't change. Everything came from within the 2 carts. That was the system. Final velocity is still a third of the original of that cart. Here's a really, really interesting application. Imagine you've got a bunch of train cars. They're all pulled tight together, and this guy needs to kind of get started. The engine needs to start pulling all the other carts. Right? These carts are all tight together. They're snug. All the connections, they're tight. But right here, it's loose. It hasn't started pulling on it. What do you think is going to happen if that train starts just taking off? Right? It's not hooked up and it starts taking off and it'll catch. What will happen?
Some engineers are going to whiplash.
Could be.
It's going to come apart. That's
Right? I'm not giving you numbers. I'm just wanting ideas. Evan was saying, I think that link is going to break. Because imagine if that locomotive starts going, it's only got a little bit of momentum, and then it's going to hook up, right? It's going to connect with the link with all the rest of the trains, and immediately it's going to have to pull every single cart all at once. And it's going to happen very quickly. So Evan, typically, you're right. It's going to start going, and then it's going to catch and just destroy the link. Right? That connection can't withstand the impulse. It would have to be a huge force really quickly to get the momentum of all of those train cars moving right away. Right? So, one solution is push backwards. You got a lot of strength that way. Get all the connections loose. Right? They're not linked up. So that way, when I start pulling the first one, I'm only pulling the one cart at that moment. I can do that. Then I got more momentum. I got to pull the second cart. That's easy to get one cart moving, and then I do one at a time. So that's a really, really odd application of momentum. Right? The other solution, what's another solution? How would I get a huge line of train cars moving? Evan, you got a thought? Throw out ideas. Yeah, okay. If that's the case, how would I get it going? Would I do it really quickly with a ton of force?
Slowly add momentum.
Yeah. If I do it slowly. If Brody's saying, hey, get all the links tight, but then have basically the same impulse, but put a little bit of force for a really long time, right? Pull really lightly for a long time. You're not going to snap that link with a little force, but it's going to take a lot longer to get everything up to speed, to put in momentum to your system, right? So again, really odd scenario, but that's ways that people think about momentum. This one, a different type of collision, elastic. Think of two bouncy balls, right? What happens when you drop a bouncy ball? Bounces back. Elastic collisions are the ones that ricochet.
That last one's inelastic, right?
Correct. Inelastic in the sense that it's like two bricks coming together. They don't bounce off each other. They just collide. And elastic, I'll always think about that bouncy ball. It's going to ricochet. It's going to bounce off everything. That's what happens in elastic collisions. They don't stick together. They bounce off each other. However, conservation momentum is still conserved. The momentum before and after is the same thing. Maggie, you with us?
I'm just been pressing snooze all
Are
day.
you with us? Okay.
One down.
So, in an elastic collision, they bounce off each other. Boing. So, cart 1 had a normal mass, but a half velocity, right? The other cart had same mass, but double the velocity in the opposite direction. Well, at the end, did you notice? Velocity 1 becomes velocity 2. Velocity 2 becomes velocity 1. They literally switch velocities. This is a special occasion where you have an elastic collision with equal masses. They're literally going to bounce and exchange velocities. Josh?
Do you know if a collision is going to be elastic or inelastic?
How do you know?
Yeah.
So, in this class, they would tell you, right? Like two objects collide and stick together. That's inelastic. That's not bouncing off. Or they'll tell you, like, there is an elastic collision between two objects.
So like
The question would tell you.
But I'm talking like in real world, like how would you know?
So
Or is that actually like more complicated?
it is more complicated. I want to explain why. It's impossible to have a completely elastic collision. It is physically not possible. This is an ideal. Again, in physics, we idealize things so that the math works, in the easiest scenario. Real physics gets really complicated. In collisions, it's no different. There is no perfect elastic collision. You can make perfect, well, you can sort of make perfectly inelastic. If you have like crazy Velcro and they stick, it's still not 100% inelastic, but it's really close. I just looked up just let me ramble for like 30 seconds. To determine how elastic, you can have like a 50% elastic, inelastic collision. There's a whole range of 100% inelastic to 100% elastic. Collisions can fall in any sort of that spectrum, right? There's something called the coefficient of restitution. It's a variable that describes how bouncy two objects would be in a collision. If you have a coefficient of restitution of 1, you have a perfectly elastic collision. They're completely bounces off each other. I'm pretty sure one of the closest things in real life is billiard balls, right? 2 pool balls. They are almost the perfect scenario for an elastic collision. The coefficient of restitution between 2 pool balls when they collide is like 0.98. Almost 100%. Almost that magic number 1. The opposite would be like 2 carts with Velcro on them. That Velcro sticks really well, so you have a really low coefficient of restitution. So the answer is way beyond this scope, but I want you to at least understand like there's no perfect inelastic or elastic. But if you do real physics, you would use a coefficient of restitution and input it into this,
Okay.
and it'll switch your answers.
Okay.
Yeah.
I figured there was something more to it, but since we're just
Yep.
an introduction.
Yep, we're doing the basic, super simplified scenarios. I wanted to just give a shout out that you can do it for real. It just gets really complicated. Okay. How about this one? Again, conservation of momentum. Object 1 has a certain mass and a certain velocity. It's got a velocity of positive 1. This guy is at a dead stop. It's elastic. They bounce off each other. They transfer momentum. They don't get stuck together and share it. They transfer it. So after the collision, what do you think is going to happen? They have equal masses. That's a big clue. What's going to happen? Think this through. Some momentum plus no momentum. What's going to happen in the elastic collision?
It's going to basically transfer the momentum.
Yep.
One that has it to the one that doesn't.
Yep. And then what's going to happen to this guy?
It's going to stop.
Yeah. They switch momentums. Watch. Doop. Again, same mass is a big thing, and we're assuming this is completely elastic. 100% of momentum is able to be transferred. If that's the case, do your algebra. The velocities basically switch again. This is a golden scenario of elastic and equal masses. They're literally trading momentum. How about this? Right? What mass, velocity, double mass, no velocity.
It's going to do the same thing the last one did, except only go half as far.
Bingo. Half the velocity, yes. But you're exactly right, John. Oh, wait. So, this is one that gets tricky. This is a new scenario that we can't assume that it's going to transfer right away. We have to conserve the momentum. But we can't solve this. It's not the golden scenario of same mass, elastic. We need another equation. You need another equation to solve this. By the way, this is what I was struggling with on your homework.
Oh.
You need to do conservation of energy. right? Because I can't figure this out. I would either have to test it experimentally or I need to find another equation.
What's this?
Remember your basic algebra? If I have one equation, two unknowns, unsolvable. If you have two unknowns, you need two equations. Where do you get the other equation? Energy. We've done this before. 1/2 mv squared, 1/2 mv squared, before and after. Well, initially, this part was at a standstill, so cut that out. Again, it gets ugly, I understand. But you need to know this process. You can't tell for sure from the equation. You can't assume things. So you got two unknowns. I need another equation. That other equation is going to come from, hey, I know in an elastic collision, I'm not losing any energy. Nothing's coming in or out. There's no work being done, so there's no energy change. So the kinetic energy, also, potential energy is not changing, right? They're not moving to a different height. There's no springs involved. The only energy you have is kinetic. Well, just do before and after. You get two equations. It gets kind of gnarly. Once I have these two equations, then I can combine them, right? You would solve for maybe one of the variables, V2, plug it in here, solve this in terms of just V1, you get your answer, then plug it back in, solve for the other one. And then you would get your final answer. These are where it gets tricky. Do you see that conceptually it's not hard? Conservation of momentum, plug in what you know. Conservation of energy, plug in what you know. It's the algebra that is hard. That's the only thing difficult about this. Again, this is what I had problems with on your homework, because this gets gnarly. I honestly don't know how much AP is going to make you do both, two systems of equations and solve. I hope not. Maybe once, or I don't know. You never know with AP. So, yeah, that one. Yeah, this example, this is why if you get hit by a big car, you're in trouble. Watch what happens. Say you're in this car. You're at a stop sign. You're completely stopped. Some ding-dong behind you isn't paying attention. They come flying in, they rear-end you. See, they literally smash you and propel you forward. That's when you get whiplash. When you snap your neck.
You want to put parking brake on.
It would help, right? It would resist. But that's also why you have headrests. Your headrest exists for this reason. Yeah, if you get hit from behind, your body is inertia. It's wanting to stay there while your car gets rammed forward. Well, you're going to get whipped backwards. If you have a headrest, you get pushed forward. Not like this and snap your neck. You push everything forward evenly. That's why a headrest exists.
I've never used it.
Huh?
I've never used it.
Your headrest?
Boy,
Wait, what do you mean you haven't used it?
like I never put my head on it ever.
I use
Oh.
money as a headrest.
Well, most people might not put their head on it, but even if you have it, vertically,
It's there.
if it's still there, it's going to prevent your head from going like this.
Your body's going to stop.
But it's going to go back a little until it hits and then move it forward evenly. So it reduces that strain. Again, a lot of physics goes into engineering and making good products. Right? There's a lot of really cool uses. Even if you don't go into engineering or sciences, this is really cool to know and to be able to think through, why do I have to wear this stupid seatbelt? What is this thing doing from me?
Stopping you from flying through a windshield.
Yeah, bingo! It's stopping your inertia from killing you. Right? It's cool to know kind of these answers and...
How do you get shot, under there, or you go on your windshield?
Wait a
Yep.
second. So if you hit something on impact, you didn't have your seatbelt on, is there a delay from when airbags deploy?
Yeah, there is,
I
of
didn't know,
course.
like, theoretically-
It's really short.
I didn't know if it was like theoretically like if you hit something if you weren't wearing a seatbelt. I'm not trying to advocate not to wear a seatbelt, but like
Which you
is it
never
possible-
should advocate for that.
Yeah, but I'm saying like, is it possible your airbag would just like catch you and like throw you back
Yes,
into the seat?
yes.
But
But you could slip, like if you're going upwards in the airbag, you could glance off it. You could slip underneath it. Also, the airbag, seatbelt are meant to work together, right? You don't want to rely on just one. The seatbelt stops you, but also keeps you here. The airbag is what it's mainly to stop you from going into, your steering column.
Oh, because it would also be bad if you like, because you're not supposed to be close to the airbag when it deploys.
Yeah. Have
So
you
if
heard
you,
of
like,
people
bounce-
getting injured from airbags?
Yeah.
Think about why.
Yeah.
They inflate so quickly. Think about an impulse. What happens if you're up close to your airbag and that thing goes off?
It's gonna be just like
You're gonna break something,
Not only is it really, really fast, right? It's got a certain amount of force. If it applies that force really quickly, you have a huge impulse. That's going to hurt.
Wait, so if you're really short and you have to sit really, really close to your steering wheel, does that mean
It's gonna
that
hurt worse.
Does
Yeah.
that mean you'd pretty much be better if to like shut off the airbag?
No.
Because if the airbag deploys
Definitely
and
not.
You're like really close to it. That would just probably end up.
I
killing
mean,
you, wouldn't it?
No, it's not going to kill you.
It's still going to do.
It's a
less
big
damage because
balloon.
It's still a lighter, like
Yeah.
a lighter.
Yeah.
The only thing it will do is probably break your nose.
Yeah. It will hurt you, but it'll break your nose. It could bruise your ribs a little, right? If it impacts
Do you
you.
want to have a broken nose, or do you want to fly out the windshield with a lot of glass?
Yeah, it will hurt, but not nearly as bad,
Because,
right?
like, they just said,
Also, that's another reason in driver's ed, I remember this, I try to do this. You should not have your steering wheel pointed up at your face, right? Don't crank your steering wheel and drive like this, because your airbag is pointed up. Well, guess what that's going to hit?
base.
You want your airbag pointed, your steering wheel pointed, the surface, perpendicular to your chest, so that when your airbag in your steering wheel goes off, it hits your body. That's what you want to stop, not your face. Huh? Yeah, there's a lever that you can take your steering wheel and move it up or down. Right? So some people undo the steering wheel, they pull the button and let it flip up. They can get in the car really easy and then they lower it back down. And then they drive. When they get to the store, they lift the whole steering wheel, they let it flip up, and they get out really easy, and they do it every time.
There's even some like telescopic.
Personal preference.
There's even like telescopic steering wheels, like they'll
Yep,
go out.
yeah.
or whatever.
Most cars, yeah. That's another thing. You don't want it up against you, right? Because then it's going to basically be shoving you into your seat.
Yeah.
But you also don't want it way far out because the airbag might deploy, and then you still have time to move forward and collide. So you got to balance. But anyway, enough about that. Questions about conservation of momentum.
Shut off your airbags.
There's two scenarios. What types of collisions do we got? What are the two types? And inelastic. Inelastic is the sticking. They collide and get glued together. They're now one object. The mass is m1, m2, and they have a single velocity. Is conservation or momentum conserved in an inelastic collision? Yes or no? Did we do calculations for inelastic? Yeah, we did. Momentum is conserved in inelastic collisions. However, the kinetic energy is not. That's a key thing that I want you to remember. When you have an inelastic collision, you can't use this to help you. Kinetic energy is not conserved in an inelastic collision.
Can you subtract the two and then whatever's left is supposed to
Correct. Basically, the reason is when you have things sticking together, partially it takes work to get them to stick. Something has to happen to get them to stick. Well, as soon as you do that, you've changed the kinetic energy. You can't say that it's equal beginning and end. The other thing, when they stick, there's a bunch of heat and friction. When they collide and actually go to stick, it's really small, but that sends energy out. You've lost energy. You don't have the same kinetic energy before and after. But your momentum is conserved. So I want to repeat. Inelastic, momentum is conserved. Kinetic energy is not. Please, if you're taking notes, write that down. I don't want you to get confused.
Read it one more time.
Inelastic collisions, when they stick together, momentum is always conserved. That's no problem. But your kinetic energy is not conserved. You can't rely on this, the kinetic energy, being the same before and after for an inelastic or a sticking equation.
So inelastic, your energy is preserved?
Is not.
Is not.
Inelastic collisions, you will always conserve your momentum, but you will not conserve kinetic energy. Right? It takes work to stick them together. You lose heat, that friction. For an elastic collision, you conserve both. Of course, you conserve momentum, and you also conserve the kinetic energy. That's why we can use both of these equations if we have an elastic collision. Okay? Inelastic, conserve momentum, but not kinetic energy. Elastic, we conserve both momentum and kinetic energy. That'll be key to know. AP will test you if you know that. Evan? Yes, you can.
So, inelastic conserves momentum.
But not kinetic energy.
And elastic preserves both.
Correct. Elastic, you conserve both. Okay? Double check your answer. Think through these. I'm going to have you just look at them. I want you to be quiet while you think about it. Don't give clues to anybody else. I want you to just think about it, stew over it in your head. So, first one.
Inelastic preserves both. Inelastic preserves your momentum, but not your kinetic energy.
Preserve momentum?
Yeah.
Both of them conserve momentum.
Yeah, but
Any collision, you conserve your
I thought
momentum.
you said preserve.
Either way, conservation is the actual word, but preserve is the same idea, right? You keep it the same. Okay? Okay, so I want you to think about this question. I'll give you a minute. Just think about it.
Thank you, guys.
Really apply what you know about momentum. Think about the equations. Think about what it's asking you. Right? Don't share, don't shout it out. I want you to do this individually. Challenge yourself. These are tricky. These are meant to be, oh, looks like an easy question. No. That they're meant to really test if you understand the concepts. Question says, 2 scenarios. Which one is more damaging? Driving at a certain speed into a massive concrete wall, or driving the exact same speed into another car with equal mass, equal velocity? Which one is more damaging? 2 scenarios. Red car has the same velocity in both. One time the red car hits a massive, huge concrete wall. The other scenario, that same car, same velocity, hits an equally massive car with an equal and opposite velocity.
third scenario, take the keys away from Grandpa.
Yep, so you got to tell me, think about
I think
what's going to be the worst, again, for the red car.
Lock in your answers now.
Yeah, that'd be nice. I wish I could. There's some stuff that you could do that. I'd be really curious just to kind of see where we're at and then critique it.
You can get like a
You
little
use the
box.
box as a
Huh?
button. You use Kahoot.
Yeah,
Yeah.
if I had more time, I would love to throw random cahoots for stuff like this. I'll look into that.
You can have like a little box up there, and we can all get a little piece of paper. Write our answer.
Cast your ballot.
It would be like Survivor. You know
Oh. Yeah, a long time ago.
that?
Okay. Did everybody get a chance to think about this?
Yes.
Okay, so just off the cuff, who thinks it's more damaging to hit the brick wall? Who think that one is more damaging to the red car? Quite a few. 3. Who think it's just more damaging to hit the oncoming car? Raise your hand.
You come in that building.
Who says something else? Ethan? What do you think?
I think they're equal.
You think they're equal?
Yeah.
Both scenarios are just as damaging to the red car?
Yeah.
Ethan thinks it's more
Okay.
dangerous to drive off a cliff.
Did anybody else not vote that has a thought? Just throw it out there. Toss it in the ring.
I reserve my right not to vote.
I wanted to.
You plead the fifth.
What?
You plead the fifth.
Yeah.
Andre, you have any thoughts?
I believe in you, Audrey.
The
It
man
would
should
be
just
blue
take care.
car because the momentum's like dispersed, but in the wall it's like transferred.
No, they'd be equal.
It's you just focus on the red car. Which one does more damage to that red car?
I
Well,
think you should
in
just take
both-
an Uber.
In both scenarios, the red car comes to a complete stop. So his momentum goes from the same momentum to 0 in both situations.
It's a good thought. Do we agree? Does that make sense?
I don't know. You're the teacher.
Well,
No. I'm not the gatekeeper of knowledge. Don't look to me for the answers.
We looked at.
I can tell you wrong and you can completely dismiss me. I'm not the gatekeeper of physics knowledge. If I say something wrong, correct
I
me.
think it's either equal or it's the
I mean-
top one. Because
I don't feel like it's the brick wall because the wall was just sitting there. It's not going to take as much damage as the other blue cars, probably.
You,
but if the brick wall doesn't move, I feel like that would do more
Yeah.
damage compared to like
again, we're focusing. Which one does more damage to the red car? That's the one we're driving in.
the wall.
Which scenario is safer for us? That's another way to think about it.
The wall doesn't.
Would I rather get into a head-on collision with an equal opposite car, or would I rather get into a head-on collision with a huge concrete wall?
I'd say it'd be. Yeah, I'd rather get hit head on
I'd rather
than get hit.
No,
it'd be
because-
more dangerous.
because you have your momentum going one direction and the car's momentum going in another direction.
No, wait, you might be right. Hold on.
In the concrete wall one, you just have your momentum. Concrete wall's not moving. You're going from your momentum to 0.
It'd still be a force though.
Well, yeah, no.
Yeah,
It's
so,
still
so
force,
first
but-
of all, momentum 1, both scenarios, the red car has P1, right? Momentum,
Right.
which is certain mass, certain velocity. It's the same in both. Right?
Yeah.
Afterwards,
It's
what's the momentum of this car?
0.
So P,
1 minus 1.
I'm going to do initial and final. It's 0. Do we agree with that?
Yes.
You hit that wall, man, that thing's stopping you. You're going to go down to no velocity. Your change in momentum, delta P, was
The initial minus. Or the final minus.
0 minus pi. So it's a total of negative pi. That's how much your momentum changed.
Yes.
Okay? What about this scenario?
It's still 0.
This has momentum.
It's this. No, but it's the same. Wait.
This is P blue initial, and it has the same mass,
Yeah. So it's
but
equal opposites,
negative
it's
V.
style.
right?
Yeah, it's
So if I
exactly
have my initial momentums and I add them together, what's mv plus m negative v add up to?
It's 0.
0.
Yeah.
So the final, P final,
Okay. So I'm not
is 0. That means the change in momentum for the top scenario is also 0 minus pi. Both of them have the same change in momentum.
Right.
Now let's think, what causes a change in momentum?
Impulse.
Impulse, J, is F times delta T.
Oh, that's why I think it's the top then. Maybe.
Well, think about it.
The impulse would be much higher. You have.
Well, it's a good point. The overall effect is the same in both.
Right.
Do you get that?
Yes.
This huge wall is going to stop you dead.
Mhm.
But a car with exactly the same mass and an exactly opposite mass, they're going to cancel each other out. You're also going to stop dead.
Mhm.
Right? Now the question is, do one of the crashes happen faster than the other?
No, but well.
Well,
I
okay.
feel
This
like
gets
I feel
really
like the brick
tricky.
Wall, I feel like the brick wall would stop you. But I don't know how many things we're putting in there, like how many factors we're considering. Because I feel like the brick wall would stop you quicker because it's a lot more solid than a human
It's
vehicle.
kinda like
but,
the
a
video
vehicle
is
would.
Okay, wait. So then the vehicle would still be more damaging, right? It would still be more. It would because if the vehicle is going to compress in both situations, it's going to take
That's the thing. We only care about our car, right? Remember the crumple zones? I got the same crumple zone on both. So if I hit that brick wall, it's going to crumple. It's going to take a certain amount of time for that crumple zone to crumple and stop me.
Well, I think
So I have a
since-
certain force.
Since the other vehicle would also have a crumple zone, I feel like both of them, since they're both hitting, that
Yep,
would-
exactly the same time.
It'd be expanding over a longer period of time.
Are you sure?
If you hit that wall, it's not gonna. The wall isn't gonna compress. The wall's just going to.
Correct, but we don't care about the wall. We only care about our car.
Which
care
I
about
think
the wall,
because
slam
because
it
there's
into
no because there's nothing to absorb. Like I feel like you would just do more damage to the car because
No.
hitting the brick wall. I think you would.
Right? Our car is going to crumple a certain amount, but even if we hit the other car, that car is also going to crumple a certain amount. They're going to crumple in exactly the same time until they stop. The time in both of them is actually the same.
Yeah.
These scenarios are equal to each other. Right?
I think this man's green needs to see a therapist.
Their explanation,
Clearly having
again, I appreciate your thoughts. I don't care right or wrong. I care that we actually either say like, oh, I did think about it correctly. Here's the physics that supports me. Or you think, oh, I had that wrong. Why did I have it wrong? Oh, wait. I forgot to think about this. So their explanation is talking about your car decelerates to a dead stop in both scenarios.
Right.
The dead stop is easy to see when you hit the wall. Of course you hit the wall ain't going to move at all. So your collision is going to be as long as it takes for your car to crumple. Then you're stopped. However, the oncoming car, let's see, the same is true when you hit the car. If the oncoming car had less momentum than you did, you would win, right? You'd end up colliding and pushing both of you guys backwards. Okay? You would have less damage.
Depends on the person.
Because you have more momentum than the other car, you would win and give that momentum, the excess, into that car. It would be safer for you. That's why having a big car is safe. Even if you hit at the same speed, if you got more momentum, you win.
But also, wait. But what
Can I finish really quick? If you have the oncoming car that has more momentum than you do, it wins. You're in the smart car hitting an SUV, it's going to have momentum, you're going to get shoved back. So not only are you going to stop, it's going to throw you the other way. You have a much bigger change in momentum, more impulse on you. But if they're exactly the same, none of them win. You completely negate each other. Josh, what were you going to say?
I was gonna say, like, if you hit a larger vehicle, but the vehicle was going slow just because you're going faster, doesn't mean you're going to win.
True. If you changed both momentum or the mass and the velocity, it could be, I got a little smart car,
And you hit
and I'm going really fast.
You hit an 18-wheeler going 15.
Yep.
You're still
You
gonna
could
lose.
cancel each other out.
Wait.
I feel like you'd still lose.
Yeah.
No. You're just talking momentum. That would come down to your crumple zone. Can your car dissipate a lot of momentum change?
A smart car.
A semi has a huge engine. It has a ton of time to dissipate all sorts of momentum that wouldn't really impact the driver. A smart car got about that much. That's all it has to dissipate whatever momentum happens. That's why, on paper, neither of them win. Right? Your little smart car has just as much momentum as the big semi going slow. But that's not the full picture. Your car has to somehow dissipate that momentum before it impacts your body. It's not going to be able to, and it's going to hurt you.
So what you're saying is you'd be safer to sit in a shopping cart with a bomb suit than to drive a smart car.
Bomb suit.
Yeah, like those suits, like
like one from the Hurt Locker. You
Yeah,
know, big,
right, Hurt
big
Locker.
puppy suit
yeah.
that people like disable bombs in.
Why is that safer?
Because you said there's only like
Because it doesn't. You're not making smart
Right.
cars sound very safe if they hit anything.
Right, but then now you have a way higher likelihood that anybody on the road is going to have more momentum than you. It's not an equal exchange. They're going to overpower you and give you way more change in momentum that even if you got a big bubble suit, it's got to now withstand more than anything else. Right? If you have less mass, other things will win. Do you get what I'm saying?
I think so.
Yeah, there's two different things. One of them is equal momentums, but your car's got to do something with that dead stop. Smart car can't handle that very well. The physics will work, but the effect on you is going to be bad. You go the other way and say, okay, I'll have something that can handle tons of impulse, but oh crap, I'm tiny. Something is going to overpower me, and we're not going to have an equal collision. They're going to hit me and throw me back. That's a lot more collision to handle. So that's why a really massive car that's really big is the best scenario. Because you have a lot of momentum that can negate other momentum, and your car can physically absorb a lot more impulse. Okay? Okay, last one.
Still rather hit the wall.
Actually, do you want me to save this for next time? Okay, we'll pause on. This one's a really good one.
It is better the next time.
I know.
No, I'd rather hit the sword.
Okay, so what I have for you the rest of class,
Noted.
I have homework. I'm going to post this in a second.
Could kill somebody.
You guys, I'll pass it out.
It's a small price.
For what?
For science.
So strong. They're strong. Sarah.
So this is going to be really good practice for these momentum questions, and also as we kind of look towards preparing for the test.
So what did we do?
The really tricky part that I'm wanting to help you with,
Wouldn't pendulum bob a person?
huh?
Wouldn't pendulum?
Nope. A pendulum bob is something that dangles. You're going to basically fire a bullet into a wooden block on a pendulum and let it swing. It's a really classic.
The bullet is colliding with bob at the bottom. Like, it's,
Where?
at the bottom it says while the bullet is colliding with bob, momentum is conserved.
The bob.
I know, I didn't see the bob.
Yeah, not bob.
But
So again, I want you to draw your attention. If you look, the first page, really straightforward. It's got a bunch of baby questions that are going to, not to insult you, but give you those little tiny steps to put the whole thing together.
what happens if I struggle with the baby question?
We'll have to
That's
revisit.
not good.
Right? Look at your note. Use your notes. I want to draw your attention. Look on page 2. Guys, I'm trying to help you out with that tricky part. Look at page 2. It's question 2. Specifically, D and E. Those two questions are the hardest to solve. The reason is, exactly like our slide said, remember, it's this question, if you read it, they collide elastically. They bounce off each other. So is momentum conserved? I want a unanimous answer from everybody.
Why would it
Elastic collision, is momentum conserved?
Yes.
Yes. It's always conserved, elastic or inelastic. In an elastic collision, is kinetic energy conserved?
No.
Yes.
Oh, we
Yeah.
Elastic.
Elastic. Yeah.
It's an elastic collision. So that's the key. When you answer questions D and E, it's saying, hey, what's the final velocity of both carts after they bounce off each other? You're like, oh crap, I don't know. That's where you have to use conservation of momentum and conservation of energy and solve that big mess of a system. However, ideally you would do it that way. That's the full, thorough way. Right? It's really ugly algebraically, but the process makes sense. I got a conservation of momentum and kinetic energy equations, solve them. I got 2 equations, 2 unknowns, solve the system of equations. However, they give you a shortcut. If you look at the very top of your worksheet, on page 2, the top right, they give you a really simple second equation. It's only valid for elastic collisions, so you can use that. You're going to use the conservation of momentum. That's what the equation is in the top left. And this velocity equation. you need to use both equations to solve for steps D and E, final velocity 1 and final velocity 2. Now you still, have to solve two systems of equations, but it's really easy because there's no squared. It's not 1/2 mv squared. You don't have to do square roots and all that. It's just two linear equations that you solve. So that's what I want to draw your attention to on steps D and E. Those ones are tricky. And then the final, on page 3, that one, you have to consider all forms of energy. Right? If you fire a bullet into a wooden block that's on a pendulum, guess what? It's going to swing until it runs out of kinetic energy.
Wait.
So question 3,
I know what pendulum is, but if it's wooden, wouldn't it just go through?
no, you assume that the bullet gets lodged in that wooden block. Right? I want to show you.
There's a very low chance it would just so cleanly go through it that
It would definitely.
Yeah, you assume it traps the bullet, so all of the momentum gets
Are you
transferred.
shooting at like an angle or something? 'Cause
No.
if you shoot-
Just like this. I shoot my bullet. This is the Super Mario or Mario Kart bullet, by the way, if you can't see.
Okay, so you're shooting it from the side.
It's really hard to see. You shoot the bullet into this block,
That's
and it
right.
gets stuck. So all of the momentum and energy gets transferred from this into the block bullet system.
That's why I was confused, because I'm imagining you looking at the pendulum and then shooting it like that. And it looks like from the image you're shooting it basically from the side.
Yeah, you shoot it from the side, the bullet gets lodged, and this pendulum now has motion, but it's a pendulum, it rotates, so it's going to swing up till it loses energy, and then it's going to come back down.
Well, there's even there's a lot of targets that are like that too, like metal
Yeah,
targets. You
yeah.
shoot them, and then you hear ding, and like the target.
Yeah, it swings a little. Yeah, all the energy in the bullet gets transferred more or less into that metal plate. Now, obviously, it ricochets a little bit,
Yeah.
so it's not a complete transfer,
Yeah.
but that's the idea. You let this big, heavy thing swing a little bit and then reset to absorb your bullet energy and stop it. That's the idea.
Could the bullet go fast enough that it could go clean through without
Yeah.
like
Yeah,
disrupting
that gets into more physics, like penetration, gets into like your material strength,
Mhm.
right? If your material can only absorb so much, energy before it tears, that's when your bullet would pierce through.
Okay.
Yeah, you still get some energy transfer that would swing it a little, but then in that situation, your bullet would go through. That's what armor-piercing rounds are. They're made to exceed the strength of that, armor
Yeah.
and pierce it.
Well, because so they travel faster. It's not like the materials that necessarily. Well, obviously the material has to be stronger,
Yep,
but it's because it goes so fast.
it's a lot of things.
Okay.
It could be an insane amount of energy that armor can't handle, and it would just tear through. It could be a harder material, right, that doesn't deform. It just keeps plowing through the armor and then ripping it open. It could be a bigger bullet to give more energy. It could be all of those things combined. There's a lot more science and engineering, aerodynamics, the temperature outside, all sorts of stuff that would contribute to your question. Aiden, quick question.
I suggest we watch John Wick.
Watch what?
John Wick.
Oh, that movie?
Have you never seen
Hey,
John
No,
Wick?
I know what they are, and I've heard they're good. I've never seen them.
I have it on my
Now we
phone.
have
You
to
can
watch
play
it.
I don't think it's
Is it on like Netflix or Hulu?
it's not school appropriate
It's
at all.
not.
It's
No,
Oh,
not at all.
then that's out.
It's-
I'm
We
out.
can sign a permission slip.
No.
I don't even see.
You guys might be covered. I would not be covered.
Permission slip. It's not like
I would get the boot.
It's not. Well,
Okay, guys, can I bring you back for a second? This is your homework. I want you, again, I apologize. We had really good discussion. I value that. I'm sorry I didn't give more time to work on this. This is your homework. I'm not going to be very strict on, turn it in before you walk into my room next class. We can even take some time next class to work on it a little more.
Yes.
We have some flexibility. But you need to all attempt this, right? I want you to get it done, and then certain parts be like, yeah, Mr. H, this one, I didn't know. I just left it blank and moved on. perfect. We can deal with that.
If I'm struggling
If
with any
you-
questions, I'm giving up.
Yeah, if you walk back into my room and this isn't done at all, that's when I'm going to have a problem. That's me walking a one-way street. I'm trying to teach you and you're doing nothing in return. Nothing happens if that's the case. I'm giving you stuff to do, to practice teaching you. You got to put in some effort to practice it. Not only to learn, but also to figure this stuff out. Okay? So I'm going to call it quits on the recording.